Okay. Um, uh, Hello, everyone. Welcome to the session Weather and Climate Extremes General. This is the third block of this session, which is dedicated to extreme events, their dynamics, as well as their influence on the hydrosphere. So we have 5 presentations this block. The fourth block of this session will be happening tomorrow. So feel free to check it out. I also wanted to remind you that we have 4 posters in our session. So also feel free to check them out tomorrow. Oui, bienvenue à la session extrême météorologique et climatique générale. C'est le troisième bloc de cette session. Il s'agit des événements extrêmes et leur effet sur l'hydrosphère. Nous avons 5 présentations dans cet bloc et demain, nous avons aussi le quatrième bloc et aussi nous avons 4 affiches dans cette session. Alors, je vous invite à les voir. Yeah, so to begin with, we have a presentation from Sam Anderson, which which title is Heatwave, Streamflow, and Climate Change. Where and when will the streamflow response to our anomalies change most rapidly? Sam, the floor is yours.
Okay, great. Thank you. So it should be full screen. Okay, yeah, thanks for having me. My name's Sam. I'm a postdoc at Simon Fraser University working with Sean Chartrand, and I am really interested about how short-term warm events like heat waves can influence river flows. And I approach the problem from a data-centric perspective that I'm looking forward to sharing with you today. Heat waves can really matter for rivers. And my personal inspiration for studying this was living through the June 2021 Western North American heat wave, which a lot of us have been speaking about today, where this week of temperatures rose up to 20 degrees warmer than normal. And it also drove a very highly variable streamflow response. Basins that had snow to melt at the heat wave onset responded with a rapid streamflow increase, in some cases achieving all-time record flows. Well, then after the heat wave, many basins experienced exceptionally low flows unless they had glacier runoff to act as a buffer. However, warm anomalies are a very broad category of events. And it was a couple months later, in November of 2021, a series of atmospheric rivers delivered over 200 millimeters of precipitation to BC. And importantly, this event was also anomalously warm, in addition to being anomalously wet, about 4 degrees warmer than normal as measured in Vancouver. Because it was warm, most of the precipitation fell as rain, and the early season snowpack also underwent substantial melting. So in other words, those few extra degrees did a lot of work in shaping how this event played out. So these two events were very different, but they share a similar context in that they were both multi-day warm anomalies, and their impacts were strongly influenced by their timing relative to the 0-degree transition. Their anomalous warmth was enough to favor rain versus snow in November and drive excess melt in both cases. So we can expect one impact of climate change to be that there will be a change to the periods of the year during which warm anomaly events like these can drive a streamflow response. And further, we expect there to be more frequent and more intense multi-day warm anomalies like heat waves. So given that context, today I'll be asking 2 questions. First, I ask how are streamflow responses to warm anomalies empirically linked to the 0C transition timing? And then I'll ask, how does the timing of the 0C transition change under warming? And here I'll use analytical models of temperature to derive the sensitivity of key metrics that govern the streamflow response. And importantly, I analyze these links and sensitivities across normal, warm, and hot events to understand how the streamflow response to heat waves may change differently than the streamflow response to more moderate conditions. So we'll begin by considering these empirical links in question 1. We use the Caravan dataset, of which the Canadian subset includes over 800 basins that have streamflow observations between 1981 and 2020, and that also have basin average temperature and precip derived from ERA5. We then define 3 event classes, visualized here for a single basin, where hot events are defined as being at least 3 consecutive days where temperatures exceed the seasonally varying 80th percentile of temperature. Warm events are between the 60th and 80th percentile, and normal events are between the 40th and 60th percentile of temperature. And so we can identify how all of these events in the historical record at each basin over 40 years, and we can see how streamflow behaved over the course of each event. So here's 1 year in one basin with the events of different classes highlighted. And we can calculate the increase in streamflow during each event, the event duration, and the event temperature. Then for each event, we can calculate a streamflow sensitivity defined here as beta, which is the ratio between the streamflow response and the event duration and temperature. This sensitivity is a metric that aims to summarize the overall processes acting to generate river flows during an event in a basin. And we can aggregate sensitivity beta through time for the normal, warm, and hot event classes. And so here is shown that aggregation as a time series for each event class at a single basin. And it's telling us that hot events drive streamflow in autumn and spring, or associated with large streamflow increases in autumn and spring, as indicated by this bimodal curve, while normal and warm events drive streamflow primarily a little later in spring. So these are results at one basin, but we can also aggregate over many basins to see how these patterns perform. And what we find is that this bimodal pattern appears to exist in many basins, and the key characteristics of the temporal structure have relatively simple explanations. What I mean by that is the autumn mode turns off when event temperatures transition to be sub-freezing and inhibit rainfall-driven flows. This happens later in fall for hot events, as hot events remain above freezing for later into the cold season. Then the spring mode turns on when the event temperatures rise again above freezing. So this is when melt-driven runoff can start to really play a role. And similar as prior, this timing occurs earlier for hotter, warm anomaly events. And finally, the spring mode turns off for all 3 classes when the basin snowpack becomes depleted. We can summarize the controls of the bimodal character with 3 metrics: T-, which is when temperatures drop below freezing, T+, which is when temperatures rise above freezing, and delta, which is the duration for which event temperatures are sub-freezing. So we can think about climate change then by considering how warming temperatures drive a shortening of delta, and how this reduction may be different for different basins and different event classes. So this brings us to question 2, where we'll ask, how does the timing of the 0C transition change under warming? And how sensitive is this timing to warming for different event classes? I'll start off conceptually with an idealized model of temperature, where a sinusoid here can be defined by its mean, amplitude, and frequency over 1 year. And we can analytically solve for the 0C transition timings, as well as the duration below freezing. And then we can take the partial derivative with respect to mean annual temperatures to express the sensitivity of delta to warming mean temperatures. And this expression is telling us that if average temperature is warm, then delta is reduced. So each basin is spending less of the year below freezing. And what we see is that the reduction in delta is greatest in the warmer basin. And this is because the slope of the temperature curve is more shallow at 0C. And so a small amount of warming can have a larger reduction in delta in the warmer basin. But this becomes a more powerful and useful lens when we return to our problem thinking about normal versus hot events. So a hypothetical basin might look like this, where median daily temperatures are shown in blue and the 90th percentile threshold is shown in red. And if there's a small increase in mean temperatures, for example, then there is a change in the timing of the 0C transition for both of these percentile levels. And there's a larger change in the transition timing for the hotter temperature percentile. So put another way, if there is a small increase in mean temperatures, delta 50 of the median will decrease by a small amount, while delta 90 of the hotter temperature percentile will decrease by a larger amount. And if we look at two real basins, a colder basin on the left and a warmer basin in the middle, we can fit sinusoids to each temperature percentile level from median conditions to the 95th percentile. And we can then estimate the sensitivity of the sub-zero period to warming for each percentile level plotted on the right. We can see that in both basins, the sensitivity of delta to warming becomes more negative, or it's more sensitive for hotter temperature percentiles. One key point here is that at the scale of an individual basin, the sensitivity of delta for the 90th percentile of temperature can be very different than the sensitivity of delta for median temperatures. And this implies that changes to the hydrologic responses to events like heat waves will be very different, actually, than the response to less extreme events. Looking spatially at the difference between the sensitivity at the 90th percentile versus the 50th percentile, we can see in darkest red that the coastal, southern, and western prairie regions have that greatest difference, meaning that the streamflow responses here will change more than streamflow responses to moderate conditions. Further, if we look at the spatial pattern of the sensitivity of delta for the 90th percentile of temperature, we again see in darkest red that the coastal, southern, and western prairie regions are the most sensitive to warming. So wrapping this up and tying this back to our streamflow storyline, we can see that under small amounts of warming, this is telling us that delta for hot events will reduce more than delta for normal events. And so this means that the autumn and spring modes of streamflow sensitivity may become closer together in time, and these changes will be more pronounced for hot events as compared to colder events. Essentially, this is telling us about how warm anomalies are playing a role that's becoming more enhanced earlier in spring and later in fall. And this is amplified at hotter events and hotter basins. So my concluding point is that under uniform warming, we can expect that the streamflow response to more extreme events will change more than the streamflow response to less extreme events. And so this is a paper that Sean and I have written up and is in review, and the topic has a lot more ground than I could get into today. So I look forward to chatting with you in the question period now, or feel free to reach out to me after the session. Thank you very much.
Thank you so much. We don't see questions just yet.
Okay.
So yeah, is the paper like is the preprint available like to read available to read, or is it like somewhere like in the journal where the preprints are not allowed?
It's currently, there's not a preprint available,
Okay.
but follow me on Twitter or feel free to email me, and I'm happy to share any parts of it with anybody who's interested.
Sounds good. Thank you. Let's see if there are any questions. I don't see any just yet. So, well, thank you so much, Sam. We will move onwards to the next speaker, which is Stephen Dery, who is a professor at University of Northern British Columbia. And he'll be talking about moisture fluxes during the 3 atmospheric rivers in September and October 2021 in British Columbia's upper Nechako watershed. The floor is yours, Stephen.
Thank you so much, Lisa, and hopefully the share screen is working at your end. So good day, everyone. I'm Stephen Dery, and I'm actually presenting on behalf of two co-authors from University of Northern British Columbia. So that is Tamar Richards-Thomas and Spencer Woike. And we'll be talking about moisture fluxes affecting the upper Nechako watershed, and specifically during 3 atmospheric rivers that impacted the area in September and October 2021. And so we're at the University of Northern British Columbia. This is on Pliglitene, traditional and unceded territory. Do I wish to acknowledge our funding partners, Rio Tinto, NSERC, Real Estate Foundation of BC, as well as Global Water Futures. And the motivation and objectives for this work, well, to identify primary pathways for moisture transport to the upper Nechako watershed and other interior regions of British Columbia, and then to quantify net moisture fluxes and their directional constancy. And I'll be using the term steadiness when I refer to this quantity in this presentation. And this will be obviously in the atmospheric rivers that we'll be talking about that affected the upper Nechako watershed. So why the Nechako watershed? Well, it's actually the second largest sub-watershed of the Fraser River Basin. So it's part of the Fraser, of course, very important salmon river. And the upper Nechako actually has hydropower facilities. So perhaps you can see the map on the top right here of the slide and the location of the Nechako within north central British Columbia. And indeed, the upper Nechako covers about 14,000 square kilometers. We have the Nechako Reservoir, Kenny Dam, the Skins Lake Spillway, as well a 16-kilometer tunnel from the Nechako Reservoir to the Coast Mountains, where there's a hydropower facility operated by Rio Tinto, and this supplies hydropower for the aluminum smelter they operate in Kitimat. And there's a great interest, obviously, in understanding moisture fluxes in this region, namely during atmospheric rivers. And to that end, we actually undertook a field campaign that we called the Tatsa Ranges Atmospheric River Experiment, or TRARE. This was in September and October 2021, just before the main, obviously, flooding event in November 2021. And we essentially set up some meteorological experiments. So that includes, as you see at the bottom right, at a Huckleberry Mine or primary field site, a dysdrometer, microrain radar. We had a full meteorological station and several precipitation gauges, with the focus really being on precipitation during atmospheric rivers. In addition to the observed data that we'll be using in this study, we're making use of ERA5 as well as ERA5 land data. So this is all on hourly basis. And for ERA5, we'll be looking at integrated water vapor transport, or IVT. And then for ERA5 land, we'll look at surface wind vectors, air temperature, and precipitation. And you see the delineation of the grids for ERA5 at the bottom left, and then towards the center for ERA5 land. So we chose for this study 3 events, and these were marked by relatively heavy precipitation. And they covered September and October 2021. Ranging from about 60 hours to about 35 hours. And as part of our study, we actually used 12-hour bookends at the start and at the end of the events as well. So the first thing we wanted to check was how good are the ERA5 land data relative to our observations. Now, of course, not necessarily a fair comparison. We have ERA5 land that is at 0.1 by 0.1 degree resolution, whereas our field site at Huckleberry Mine is basically at a point. And we are in a valley, the winds are constricted. So there are obviously some discrepancies between our observations and in situ data. But you see here comparisons of time series for air temperature. So that's the red lines. And then for precipitation on an hourly basis in blue, with the thin lines representing ERA5 land and our observations as the thicker lines. So generally not too bad agreement. Obviously the ERA5 land, again, covers a grid cell, typically will represent a higher elevation than our lower site in the valley setting. You see the total precipitation amounts during events 3 and 5 and 10, with about 60 millimeters for the first event we're looking at for this study, and then greater discrepancies for the precipitation totals of the other 2 events, but on the same order overall. So let's get into some of the results. And on the panel on the left, we're actually plotting here surface wind vectors. This is based on ERA5 land, and you see the vector scale at the top right there, 2 meters per second. And we have the 3 events from top to bottom, 3, 5, and 10 during our field campaign. So generally the winds are stronger as we move towards the west, which would be on the left of the slide, moving towards the Pacific Ocean. The winds were stronger at the surface during event 5, and not as strong, obviously, for event 10, as you see there, with the vectors being shorter. The background legend actually shows the steadiness. So here we're computing essentially the mean vector divided by the scalar values for the surface winds. And so that would range from 0 to 1. We are actually showing this as a percentage. And essentially, the darker greens indicate greater steadiness for the surface winds. And you do see that for event 5 specifically, we had very much some steady winds at the surface over the duration of that event. Whereas for event 10, much lower values in terms of the surface wind steadiness. So the middle panel shows now the IVT vectors computed from the surface to 300 hectopascals. And the yellow vectors indicate over the duration of the event, sites that had 250 kilograms per meter per second. So that's usually the threshold used to identify an atmospheric river. So definitely over the duration of event 3, we had AR conditions over the upper Nechako, particularly the western portion of the domain. Lesser values for event number 5, but the persistence or constancy of the direction was greater, as you see there with the darker greens. And again, much more variable IVT vectors for event 10, and the magnitude obviously lower as well. For the wind roses that you see on the right, so this is based on the observed data that we collected at Huckleberry Mine, HM. And you see the wind roses. Again, we are in a valley setting. The winds are constrained along the west-east valley here. For event 3, you see the winds predominantly from the west-southwest and stronger winds during that event. More variability during event 5 with a component as well from the southeast. And then for event 10, you do see the wind actually now mainly coming from the northeast, but again, along the valley. The K factors, or the steadiness factors for the 3 events, showing very constant wind direction for event 3 at 91%, and lower values for event 5 and for event 10 in the 60 to 70% range. Okay, so we now computed the IVT roses as well for transect going from west to east in the upper Nechako. So that's the domain you see in the top left map here. So we have 7 points, again, computed with ERA 5. And you can see from the IVT roses at the bottom left that the IVT vectors were stronger during this event. This is for event 3 from the southwest as we move westward towards the Pacific Ocean. So that makes sense. More variability as well, moving into the inland portions. P4, for instance, you see the IVT row showing more transport of moisture from various directions relative to the sites further to the west. The panel on the right here is a heat map showing essentially the steadiness of the IVT, now computed as a percentage from the west to the east along our transect. And you do see the red squares identifying very steady IVT for the events 3 and 5, averaging 85% or more essentially during those 2 events. Whereas for event 10, much more variable in terms of the IVT direction, with a low of 64% for P number 4 at the center of the upper Nechako watershed. So the next couple of slides will just focus on the moisture fluxes affecting the upper Nechako. And in this case, we essentially separated out the cardinal directions, with the south, as you see here at the bottom in green for the domain covering the upper Nechako, the red outline. We have fluxes obviously leaving the watershed from the east, leaving the watershed from the north, and influx of moisture from the west. So we separated out the moisture fluxes in those 4 cardinal directions, assigning a positive value as an influx, a negative value as a neflux from the upper Nechako watershed. And we'll compare those to the total precipitation computed as a mass flux for the entire watershed, as you see on the right. So this panel actually shows the moisture fluxes here crossing the boundary of the upper Nechako for the 4 cardinal directions. So green, again, represents a moisture flux from the south, and the positive values indicate a gain of moisture to the upper Nechako watershed. And definitely it is the dominant direction through which we have, during these 3 events, a net moisture transport to the upper Nechako. Whereas the main direction through which we actually lose moisture Computed IVT flux is from the north, as you see here, with the negative values at the bottom with the light blue curve. Perhaps what was surprising for us was actually there's not a lot of moisture being transported from west to east. So perhaps one of the hypotheses that we had was whether the main direction that we would expect influx moisture, given the proximity of the Pacific Ocean to our west, would have been from the west. But as you can see with the dark blue curve, here we have actually not a lot of moisture coming from the west, at least for these three events. And the net IVT is the red line, as you see there, and it actually does not correspond necessarily to the periods of maximum precipitation. That's the black thick line that you see on the plots. The other point to mention here is that the y-axes are different for the three top panels there. So the moisture fluxes were significantly stronger during event 3, lesser during event 5 and event 10. The bottom panel actually shows the ratio of the precipitation net flux to total IVT, and you do see large and then smaller values overall over the duration of those three events. So again, the total IVT does not necessarily mimic the precipitation flux that we saw in the upper Nechako. So just to summarize, essentially we show that there's relatively good agreement between the RE5 land data and the observations for a number of meteorological quantities, including air temperature, precipitation, and winds for Huckleberry Mine. The pathways of moisture transport to the upper Nechako occur during these three events from southwest to northeast, events 3 and 5, and then southeast to northwest for event 10. The IVT steadiness factors are greater than 85% at all points along this east to west transect for events 3 and 5, but less than 85% for event 10. And in hourly precipitation, the upper Nechako does not necessarily mimic the pattern of total IVT during all three events of interest. So thank you for your attention, and I'll take any questions. Thank you, Lisa.
Thank you so much, and thank you for being on time.
You're welcome.
We don't have any questions just yet, but I will ask a few. So when you did this campaign in 2021, did you prepare that the 2021 will be a big atmospheric river year, or was it just like a coincidence?
Yeah, you never know in preparing for a field campaign what kind of a season it's going to be, and it ended up being a very, very stormy season. Thankfully, because the years after that, 2022 and 2023, the fall seasons were not busy at all when it came to atmospheric rivers. So it was perhaps by pure chance that we did, of course, have a busy, stormy season in 2021.
Great, thanks so much.
Yeah. We had 11.
Question.
Yeah. Yep. Go ahead.
Sorry. Yeah, we have another question from the chat. I haven't seen IVT roses before. Were a good way to display AR data, so atmospheric river data. Is this something new that you and your team has created?
No, I don't think so. I think actually Nathan has a paper in 2022 that had IVT roses. So it's not a novel idea, but certainly a little bit different perhaps from what people are used to in terms of the wind roses.
Yeah, I was a co-author in that paper. Yeah, there was Alex Tan, he created, he did this, the roses for the IVT.
Yeah.
Another question is, what IVT steadiness factor indicate for atmospheric rivers?
Yeah, so the threshold typically would be an IVT vector of 250 kilograms per meter per second over the duration of 24 hours as the lowest category for an atmospheric river, correct? Of course, the shape of the moisture plume is also important in that definition, but that's why in our plots we highlighted the values of 250 kilograms per meter per second for the moisture fluxes, correct? Yeah.
And we have another question. Wow, that's a very popular question. Why start? Do you think the IVT is initially used for just for moisture transport into the region before it precipitates, hence the lag? I found that in my extreme precipitation periods in Eastern North America via similar moisture budget analysis.
Yeah, that's a very good question. And yeah, I guess, you need moisture to create precipitation, right? So you do need a net flux of precipitation into an area. And I think our next step is really looking at moisture convergence and not just obviously the transport of moisture into the domain of interest. And that would be a better indicator, obviously, of any precipitation that falls out from the atmosphere. So that's our next step in terms of analyses with this work.
Great. Thank you so
Okay.
much for this presentation and answering the questions.
Thank you.
The next speaker we have is Hannah Lewis, who is a master's student at the University of Alberta. And Hannah will be speaking about modeling in a warming world, marine heat wave drivers in James Bay in Canada. Okay, Hannah, you have 30 minutes. Go ahead.
Hi, thank you. Yeah, as per your introduction, I'm Hannah. I'm a master's student at the University of Alberta, and my supervisor is Paul Myers. Today, I'm going to be, I guess, switching it up from the talks in this session, talking a bit more about oceanography and going to the other side of Canada, talking about marine heat waves in James Bay. So with that, I'll give a bit of an outline of what I'll talk about. I'll give an introduction to the study region and the questions that we want to look at. I'll define what a marine heat wave is, and then talk about our numerical model and how we can use this model to look at marine heat wave drivers. So to start off, the area that I'm working or studying in is James Bay in southern Hudson Bay, which, if you zoom in on this map, is this region right here. Shown in the red circles are the Cree and Inuit communities that surround James Bay. And this project kind of started off when the Cree and Inuit communities started to report and notice these very drastic changes in the marine environment. So they reported such things as a very sharp decline in the eelgrass population. They reported warmer and shorter winters, and as well as erratic and unpredictable weather and sea ice patterns. It was such that their traditional methods of predicting things like sea ice conditions and weather had started to fail. So these reports started coming in the late 1990s, and this kind of kickstarted a project to look at what is causing such a change. Also compounding this, I guess, like research or this risk is the lack of data and in general, the lack of research in Hudson Bay is causing like a lack of climate services, like long-term projections or seasonal forecasts. So this is compounding the risk that these communities already face, which they kind of rely on the sea ice in the water as a way of life. So my part in this big project is looking at marine heat waves. And I guess I should kind of define what a marine heat wave is. It's very similar to an atmospheric heat wave. It's pretty much the definition is copied and pasted. So it is a discrete and prolonged anomalous warming in a specific location. The main part of this is the anomalous warming. So you define this relative to a base climatology and a high percentile threshold. So generally we take the 90 percentile and the 30-year climatology. And again, it should be prolonged. This is generally taken to be 5 days, but can be modified to relevant ecological processes. And you should also define some way to discretize two marine heat wave events. Next, onto the dynamics of marine heat waves. This equation shown here is describing the temperature tendency of the mixed layer depth, which is the surface mixed layer. Two main components of this are the air-sea heat flux terms and the horizontal advection term. There are smaller terms that are kind of clumped together in the residual part, such as the vertical mixing, as well as like upwelling, downwelling. They're all kind of showcased in this picture here. But in most cases, they tend to be quite small. So for our purposes, we will just be looking at the horizontal advection and the air-sea heat flux. So that brings us to the numerical modeling. how can we use these models to help us understand marine heat waves and their dynamics. In our lab, we use the NEMO model, which we have our own configuration for the Arctic and Northern Atlantic at 1/4 degree resolution. It also includes things like sea ice, tides, rivers, and atmospheric forcing. For the sake of time, I'll just be focusing on one experiment that we ran, which uses NEMO 3.6. It's coupled to the LIM2 sea ice module. Our years are from 2002 to 2022. And we use the Canadian reforecasting atmospheric forcing set, the CGRF. And the goal for this presentation is to kind of determine the most influential marine heat wave drivers that we are seeing in James Bay. So to do that, we can look at the sea surface temperature anomaly, which is shown here in the plot. So this is the SST minus the daily climatology for the 20-year period. And we already noticed some potential marine heat wave events. And right now, I'm just going to focus on the notable spike that we see in 2017. So if we expand that axis and just look at the year 2017, we can kind of see a very prominent marine heat wave that persists starting pretty much as soon as the ice melts, all the way until late fall, beginning of winter. Going to that equation that I mentioned earlier, we can look at maybe what's causing this by breaking it down into the terms and using the model to calculate each term individually. So on the left, we see the heat transport that's going in and out of the bay. Negative is indicating into the bay, positive is outwards of the bay. So in 2017, again, we see a very large import of heat going into the bay. And on the right is that calculation of that one term, which again, negative is indicating heat being advected inwards into the bay. Again, if we expand that axis and look at just 2017, we kind of see something that I wasn't really expecting, which is most of this heat is being transported inwards at the beginning, or towards late fall, early winter. So probably not causing the onset of the marine heat wave that we see very early on in the season. So with that, we should look at the other term of the equation, and we can calculate the air-sea heat flux, which is composed of the turbulent fluxes like latent and sensible, as well as the radiative heat fluxes. So this is showing the latent heat calculated. And again, we see a very large, strong signal of latent heat in that year. And again, not really what I was expecting, but it is showing that very late in the fall, early winter, there is a large spike of latent heat. Negative is indicating it's going from the ocean to the atmosphere. So I guess that kind of makes sense. Because the atmosphere is a lot colder than the ocean at this point, it's kind of helping with the demise of the marine heat wave, trying to take heat away from the ocean. So finally, that kind of leaves one piece left to look at, that is the radiative heat fluxes. For the time series, we have this, but we can also look at it a bit closer. In 2017, we see that this is probably likely a strong candidate for the start of this marine heat wave. We see that the net fluxes are quite high, positive, indicating that heat is going from the atmosphere to the ocean. And then again, towards wintertime, we're seeing that the radiative fluxes are helping in the demise of the marine heat wave. So with that being said, this was a short presentation, so I just wanted to focus on one experiment. And from that one experiment, we saw that in 2017, the radiative fluxes was likely the main driver of that marine heat wave in James Bay. And later on in the fall, the heat transport and the advected heat that was probably coming somewhere from northern Hudson Bay helped in prolonging this marine heat wave all the way until early winter time. So I guess the next steps would be to do the same analysis for other marine heat waves throughout this time series and for other experiments with different configurations and compare these dynamics with each other. And with that being said, I wanted to thank you guys for your time, and I'd be happy to answer any questions.
Thank you so much, Hannah. While we're waiting for questions to pop up, I actually wanted to ask one thing. So when you define marine heat wave, so you said like essentially it's the atmospheric definition was taken and applied to the marine to the marine temperature. Sorry, I'm quite tired after a day of conferencing. So like is there any considerations in these metrics for the kind of prolonged period of time, or like should the heat wave be like, so like usually we say like after 3 days then we define a heat wave. Isn't the marine perspective the same kind of that it should be 3 days, or should it be like longer? Like, is there any considerations for longer influence from the temperatures to the, for example, marine life or something like that?
Yeah, I think that's a good question. Mostly what I've seen in the literature so far is, I think, more longer timescales, like at least 5 days. I'm not sure if that's just due to like the heat capacity of the ocean, and the ocean can stay hotter for longer, I guess. But I think, yeah, I don't know. I would like to do something with a timescale that's more ecological based, like especially in the James Bay region where the eelgrass is so important in such like a big carbon sink. I'm not quite, familiar with like the biological aspects, but I think that would be something important to do.
Yeah, that would be great. I don't see any questions in the chat, but I want to remind our listeners that you can ask questions in the Q&A part as well as in the chat. If you put your question in the chat, the speaker can see from whom the question was and can answer it directly. So with that, we are moving to the next presentation from Vanessa Foord, who is a research climatologist at BC Ministry of Forests. And Vanessa will be talking about drought, something different from the atmospheric river and marine heat wave. Vanessa, the floor is yours.
All right, thank you. Just checking that you can see my screen and hear me okay?
Yeah, all good. Yeah, all great.
Perfect. Well, thanks very much. So yeah, I'm going to be talking about meteorological drought in British Columbia. Just want to recognize some of my co-authors on this work. So Brian Mood with the University of Saskatchewan, as well as some colleagues from Stantec Consulting who helped initiate the work. So for those who might not be familiar, parts of British Columbia are currently experiencing drought. If you're in British Columbia right now, this is notwithstanding the rain that some of the province has received in May. Certainly that hasn't relieved the drought, but this product from the Canadian Drought Monitor hasn't been updated yet, to the best of my knowledge. I work mostly in northern British Columbia, so I will be speaking mostly about drought conditions in the north and partly how that relates to forestry impacts. And just wanted to point out that area of D4, or exceptional drought, that is in the Prince George area, which just happens to be the town in which I live and work. So we have been experiencing severe to extreme droughts more frequently in recent years in British Columbia. For northern BC, this really isn't normal for us, and it's having adverse effects on our forests, especially in northern BC, where the growing season is actually the wet season, and our systems just aren't adapted to these drought conditions. So one of the indices that I like to use when looking at meteorological drought and trying to relate that to forestry impacts is an index that includes evapotranspiration. So I do like the Standardized Precipitation and Evapotranspiration Index, or SPEI. I recently participated in a North American Drought Monitor conference a couple weeks ago, and luckily they did recommend that this is one of the best indices to use when trying to understand meteorological drought for Canada. So drought categories defined here as below -1 of an SPEI being a moderate drought, or the kind of orange to red colors on this graph here, which comes from the SPEI Global Drought Monitor database. It's a fun little gridded product where you can zoom in anywhere on the world and look at your SPEIs at different timescales. And then below -2 being defined as extreme drought, or those dark red colors on the map. So I'm showing here a 6-month SPEI over last year's growing season, so April to September of 2023, where you can see most of the province of British Columbia was under severe to extreme drought. For the central interior of the province, using data from Environment and Climate Change Canada Weather Station in Prince George, showing the long-term deviation from average precipitation, that this is also a cumulative drought for this part of the province. You can see that since 2010, overall conditions have been below average in annual precipitation. Some years have been 100 to 200 millimeters below average, which is 20 to 40% of our annual precipitation, so fairly significant precip deficits. So as I mentioned, extreme drought in the central interior of British Columbia is uncommon. Again, I'm using SPEI data here from that global database website. 3 months to represent a time series of seasonal drought for the central interior. Reminding you that -2 or below represents extreme drought. You can see that that blue line historically doesn't dip below -2 very often. When it does, it's actually been in the winter. We've only experienced below -2 in the summer once, and that was back in 1958. We had never experienced a fall extreme drought until 2022, and then immediately following with 2023, both of which were directly related to some of the extreme wildfire seasons that we've had in 2023 and starting spring of this year. Also, if you look at the last decade or so, you can see that the central interior of BC is experiencing more frequent moderate to severe drought in recent years. So we're seeing a lot of impacts to our forests. Part of the rationale of this work is to really understand how meteorological drought relates to ecological drought in terms of forest impacts. So we're already seeing things like widespread tree mortality, dead branches and needles, plantation failures. So this is tree seedlings that are planted following harvesting being damaged or suffering mortality due to drought. A massed year of conifer crones. So this is actually a pretty cool landscape level expression of drought conditions we saw in 2022 in response to the 2021 heat dome and subsequent drought that followed, where basically what conifer trees do if they're drought stressed is they produce a bunch of cones. And this was seen throughout the interior of the province in 2022 following the drought of 2021. Lots of dry soils, the buildup of dry fuels, and also reduced photosynthesis. So we do have one carbon FlexNet tower in the central interior, which is measuring ecosystem gas exchange. And we have seen that in our drought years, this ability to photosynthesize and uptake atmospheric carbon dioxide is reduced when the system is drought stressed. And then also drought stressed trees are related to secondary disturbances such as wildfire, insects, and wind throw. So this is showing on the left 2023 ecological drought. So this is representing an aerial survey of forest-related impacts. The red dots are tree mortality, and the orange dots are just expressions of drought, whether that be a discoloration or other symptoms. You can see for Northern British Columbia, there's not a lot of points, but just a reminder for 2023, for those of you that are not in the province of British Columbia, most of the northern part of the province, much of the northern part of the province was under the impact of wildfires, and most of the northern part under the impact of smoke. So these surveys weren't able to be conducted. In general, what we see across northern British Columbia is that our growing season precipitation is declining at the same time as our growing season temperature is going up, resulting in a loss of moisture during the growing season for our systems. So we wanted to develop our own SPI drought atlas in BC in order to better relate it to the impacts we were seeing in forests due to meteorological drought conditions. So we developed a 10 kilometer squared historical 1950 to 2023 SPI database. We used monthly min and maximum temperature and precip from ERA 5 land reanalysis data. We calculated SPI at intervals of 1, 3, 6, and 12 months. We calculated our potential evapotranspiration using the Heatwaves method. For those of you that are familiar with AT, there's a bunch of different ways it can be calculated. We also added a latitudinal correction as recommended for BC, following the methods for the Climate BC model, if folks are familiar with that. Source code for our calculations is available on GitHub if anybody's interested. We also created projections, but I'm not showing those today as I haven't had a chance to go through them yet. For the historical trends, we did a Mann-Kendall test, and we used a baseline of 1961 to 1990, and we did attempt to do some verification using Environment and Climate Change Canada's adjusted and homogenized Canadian climate data set, although that data is fairly limited across the province. I think there was only 7 stations we could use for that. So here are some of the results. We are working on publishing this, but we're not there yet. So showing winter, spring, summer, and fall, 1950 to 2023 BC seasonal drought trends. So the orange are the colors that's trending towards drought. The green are the colors that's trending towards pluvial. Pluvial is the opposite of drought. So in the winter, you can see that's where we have the greatest trends. The hash lines are statistically significant, increasing drought occurring in the southern part of the province. In the spring, there's really only an area of statistical significant increase of drought in the southern interior. In the summer, there are, again, parts of the southern interior of the province trending towards increasing drought, as well as parts of Vancouver Island. The northwest coast and parts of the central Rocky Mountains are trending towards pluvial conditions. And in the fall, there isn't really any statistically significant trends, which really isn't too surprising. Falls in BC and in most places can be quite variable in terms of weather systems. Just showing a couple more graphs. The first one on the left is looking at an SPI 6-month trend for the cold season, so October to March. So some trends towards increasing drought, statistically significant for Vancouver Island. And then when we look at the growing season, it's only the northwestern part of the province that is seeing a trend towards wetter conditions or pluvial. I thought for fun, maybe I would just pick out the 1-month SPI trends that showed both the droughtiest and most pluvial conditions, June being wetter and October trending towards drier. So the last part of this project was just to relate that SPI database to teleconnections and extreme drought. So we used that database and SPI values of equal or below -2 and looked at the Pacific Decadal Oscillation, the Pacific North American pattern, the Arctic Oscillation, and the El Nino Southern Oscillation. We looked at conditions 12 months prior to the extreme drought, and we used a k-means time series cluster analysis to break the province into the Northwest, Northeast, and Southern, South Central. Sorry, just my last slide. Here are some of the results of that work to look at teleconnections and extreme drought. I know this is a pretty messy slide here, but if you just follow me, we'll look at the top left corner first. So the AO is the Arctic Oscillation, and that top row is the 1 month SPEI. And the darker colors represent statistical significance. So you can see at the time of a 1 month drought, the Arctic Oscillation relates positively in the Northeast, and 4 months prior, the 1 month drought is related to the negative phase of the Arctic Oscillation. With ENSO, there's not a lot of trends with the 1 month, but as you can see, if we get a 3 month drought, there are some statistically significant trends with the positive phase, so El Nino and South Central, as well as further out in time with the Northeast and Northwest in a La Nina phase, which is kind of interesting. What I found most interesting is with the Pacific Decadal Oscillation, all the trends are negative, really showing that during the cold phase of the Pacific Decadal Oscillation is quite well related to drought in BC. There's especially a lot of statistically significant trends in the SPI 6 months and 12 months. So just showing that a cold PDO phase is really important for parts of the province in relation to extreme drought. And that's it. Next steps are to explore this further, to relate to forest drought impacts, and explore potential predictability of teleconnections related to extreme drought.
Great, thank you so much, Vanessa. While we wait, if there will be any questions in the Q&A part. I was wondering, so like in the beginning, you were showing this SPI product. It looked gridded. So what data set was it using like under? Because you said like you are creating the one based on ERA 5, but what was the other one based on?
That's a good question, and I can't remember off the top of my head, but it's a very well documented website. And the reason we didn't want to use that product alone, even though it is quite a fantastic database, because we will be using these drought conditions related to forestry impacts. And so we wanted to make sure we had something available for the province, and we weren't relying on an international product being created elsewhere.
Sounds plausible, thank you, yeah. I don't see any questions in the chat. So, but if you want to ask Vanessa a question, please feel free to use the chat box or even Mobi platform. And with that, we'll be moving to our last presentation from this block, which will be given by Eliott Roocroft, who is a PhD student at University of British Columbia. And Eliott will be speaking about comparison of the association between waviness metrics and extreme temperature values and future trends of association. Eliott, the floor is yours.
Yeah, can everyone see my screen and hear me and stuff?
Yep.
Perfect, yeah. So my presentation is on the comparison of the association between waviness metrics and extreme temperature values and looking at future trends of association. I'd like to thank my co-authors, Dr. Rachel White and Valentina Radic, and also my sponsors, which are NSERC and MyTact, which are in conjunction with BC Hydro. So moving on to the background. So for the background, with climate change, there's been an observed increase in the frequency and intensity of extreme events. However, the causes of frequency and intensity change are still unsure, with both thermodynamical and dynamical changes having an impact. And whereas the thermodynamical impacts are well understood, rising temperatures due to global warming will lead to more heat extremes and less cold extremes, there's actually lower confidence in the dynamical impacts on the future change of frequency of extreme events. So this is especially true when you look on a regional scale, where dynamic forcings exert a strong control. And the mid-latitude is one such region that is especially controlled by dynamical impacts. So for the mid-latitudes, the upper tropospheric circulation is dominated by the jet streams, which are these sort of strong, narrow bands of fast-flowing westerly winds. Now, these jet streams are seen as a sort of like governing influence on the weather experienced in the mid-latitudes. Typically, they are zonal, but you can get these north-south meanders, which are known as like Rossby waves, which can also be quantified as atmospheric waviness. So when atmospheric waves become particularly large amplitude or quasi-stationary, which means that they remain in one place for many days, this favors the occurrence of extreme weather. And numerous studies have proposed that an increase in this atmospheric waviness will lead to an increase in weather extremes. However, how do you quantify this connection between atmospheric waviness and extremes? So the main issue is actually that there's a large number of different metrics that can be used to quantify waviness. These encompass different variables, different heights in the atmosphere, different characteristics of the wave, etc. And whereas the connections between waviness and extreme weather for individual waviness metrics and particular regions, these different metrics may have different strengths and signs of connection. So the main aim of this study was to compare these commonly used waviness metrics and quantify the links to daily surface temperature extremes across the Northern Hemisphere mid-latitudes, focusing on summer heat extremes and winter cold extremes, with an overall aim to sort of create a robust template for which atmospheric waviness metric to use when you're looking at investigating current and future atmospheric waviness and its impact on extreme temperatures. So in order to look at the connections between high waviness and extreme temperature, we use what's known as the probability ratio, which is given by the formula here. And it's simply the ratio between the probability of a high waviness day, defined as the top 25% of days, which coincides with an extreme temperature day, which is the top 5% of waves and is given by px wave. And it's the ratio between that and the probability of there being an extreme temperature day on any day, which is the top 5% of days. So it's like 0.05. So what this gives you is the improved chance of there being an extreme temperature day during a day with high waviness compared to just selecting a random day and it being extreme. The data that we used was the ECMWF ERA 5 daily temperature and waviness values for the Northern Hemisphere mid-latitude region between 1980 and 2015, looking at maximum temperature associations in June to August, or JJA, and minimum temperature associations in December to February, or DJF. So here are the results for the probability ratios of maximum temperature in JJA for the various metrics. So what you're seeing here are the different metrics used and the probability ratios. So a probability ratio of 1 means there's no association, i.e. the probability of a day with high waviness also having an extreme temperature is the same as any day having an extreme temperature. Anything greater than 1, which is the purple colors, means that you're more likely to have an extreme temperature day when you have a day with high waviness, and vice versa for less than 1, which are the green colors. The stippling refers to the bootstrap resampled data set. So if the 95% confidence interval of the data did not cross the null value, which is PR equals 1, then the results are assessed to be significant. Overall, you can see that metrics typically have a positive association between high waviness and heat extremes with a probability ratio of greater than 1. But all metrics do have some regions of negative association, highlighting that the concept of local high waviness being associated with a high probability of extremes is not universally true. And this is also seen in the associations with minimum temperature extremes in DJF. Now, these results show overall more regions of negative associations and a greater difference between the metrics. And the distribution is seen to be different to the JJA hot extremes, which is likely at least partially due to the mechanisms that form these hot and cold extremes. So both hot and cold extremes are highly associated with atmospheric blocking. And while hot extremes form mostly below atmospheric blocks due to the increased radiative heating seen there, cold extremes are more typically located on the lee side, on the eastern side, due to cold air advection moving southward from the Arctic region. Which leads me on to one of the metrics, which is the local wave activity, or LWA. So due to the interest of time, I'm not going to be explaining all the metrics in depth. However, this particular metric has an interesting feature which relates to this mechanism of temperature extreme generation, in that this metric, which is calculated on 500 hectopascal geopotential height anomalies, gives at each longitude and latitude a measure of the extent of and magnitude of the geopotential height anomaly, both to the north, which is also the anticyclonic wave movement, and is shown by the red area on the schematic, and the south, which is the cyclonic part of the wave, and is shown by the blue area on the schematic. So when you So in the previous results, the anticyclonic and cyclonic anomalies were combined to give the overall local wave activity. But what these figures show is the probability ratios between high waviness and extreme temperature for these separate components. So you have your maximum temperature JJA associations on the left and minimum temperature associations on the right in DJF for LWA at the top, and then the anticyclonic wave in the middle, and then the cyclonic local wave activity at the bottom. And as you can see, by splitting the LWA into its separate components, this gives a much improved association. So the anticyclonic and cyclonic LWA show strong associations with hot and cold extremes, respectively. This agrees with the link between mid-latitude anticyclonic activity, especially these persistent anticyclones that form the basis of atmospheric blocking and hot maximum daily temperatures, and also the mid-latitude cyclone activity links with cold temperature extremes. So to conclude, these results show that the different metrics of atmospheric waviness have different strengths and sometimes directions of association with surface temperature extremes across the Northern Hemisphere mid-latitudes. This association for these metrics is very region, seasonal, and extreme type dependent, which highlights a need for care when trying to link hemispheric-wide waviness studies to temperature extremes on a regional scale. And therefore, studies on projected changes in waviness need to consider any potential sensitivity to metric choice when they use changes in waviness to imply changes in extreme temperatures. But also, is there any particular metric which stands out as having a particularly strong association with extreme temperatures? And the answer is yes, the LWA, especially when it's separated into its anticyclonic and cyclonic components. So what this figure shows here is which metric has the highest probability ratio for each latitude and longitude grid point. And it's mostly anticyclonic LWA for hot extremes, which is the top figure, and cyclonic LWA for cold extremes, which is the bottom figure. And therefore, for further applications of waviness metrics and extreme temperatures, especially on hemispheric or global scales, we recommend the LWA anticyclonic and cyclonic, respectively. And that's what we're going to be using for the next part of the talk, which is going to be looking at the future associations between waviness and extreme temperature. So moving on to the future associations part of this presentation. So this is a bit more speculative, and it's something that I'm just sort of getting into. But as previously mentioned, there is lower confidence in the dynamical impacts, such as waviness, on the future changes of frequency of extreme events. So it'll be interesting to see how the association between high waviness and extreme temperature changes in future prediction, i.e. will extreme temperature become more or less associated with high waviness by the end of the century? So for this, we're using the CESM2 large ensemble to compare the probability ratios between waviness and extreme temperature values on daily timescales between the future period, which is 2065 to 2100, under the SSP 3.37.0 forcing, and our current period of 1980 to 2014. So the first step to actually look at is to compare how well the association between waviness and extreme temperature is exhibited in the CESM2 large ensemble climate model compared to the reanalysis era 5 model. So what you see here is the probability ratio for the anticyclonic LWA and maximum temperatures in JJA for the CESM historical period, which is 1980 to 2014 at the top, and for era 5 probability ratio for the same time period below. And then you have the comparison. So the comparison figure is the CESM model divided by the era 5 model for any probability ratios greater than 1. So anything in the comparison figure above 1, which is colored pink, is more strongly associated in the CESM model than the era 5 model, and vice versa for the green. So for example, if the value is 0.5, that means that high waviness is half as associated to extreme temperature in the CESM model compared to the era 5 model. So as you can see, even though there are broad similarities in the spatial distribution between the CESM and era 5 figures, there are some noticeable differences, especially around Europe and the Mediterranean, where the era 5 data has a significantly larger probability ratio, which is likely due to various factors such as soil moisture feedbacks. Also, there are some strong differences in the oceans, which is especially true in the cyclonic LWA and its probability ratio with minimum temperatures in DJF. So again, there are some broad similarities over land, but over the oceans, the era 5 probability ratio is much higher, which suggests some strong biases in the atmosphere-ocean coupling. for the climate model. But if we do take the CESM2 historical period and compare it to the future period to see how the association has changed in the model over the 21st century, then we get something like this. So these figures are the same as the previous ones, but now we are comparing the future period below to the historical period at the top, and the comparisons in the pink colors means that it's becoming more associated with temperature extremes in the future, and in green it's becoming less associated. So for heat extremes in JJA, the anticyclonic LWA, again, it's spatially very consistent, and there are regional changes. The Hudson's Bay area, for example, sees a fairly strong increase in association, and there is quite a lot of regionality in the trends, whether it's increasing and decreasing in association. And overall, it's quite a small relative change in association for heat extremes in JJA. But for cyclonic LWA association with DJF cold extremes, you see a much stronger, more consistent reduction in association by the end of the century, which suggests that cold extremes will become less associated with high cyclonic waviness activity by the end of the century, which could be really interesting. But like I said, it's still ongoing work and analyzing what these figures are showing and why they are showing what they are. And I'll wrap up there. Thank you very much for listening. They're the references. Are there any questions?
Great, thank you so much, and thank you for being on time. Let me double check if there are any questions. None so far in the Q&A. I'm sorry, I don't have any questions about the cyclonic metrics, because these things are yeah, but it was very interesting presentation. So the only thing, which again I might have just missed, but did you like look at the trends of this cyclonic, like of this, like these metrics, or like these like waviness metrics, or not? Again, I might have missed that.
The trends like between 1970 and 2015, like sort of.
Yeah.
No, well, it wasn't the focus of
Okay.
this work. So we did sort of like look at it a little bit, but overall it was more to do with taking the years as a whole. So taking the time period as a whole. When you're doing the comparisons,
great.
when you're doing the comparisons.
Yeah. Yeah, that would be interesting to know how much they like, if the trends are changing overall or not. Yeah, there is a question. Do you see changes in waviness in the projections?
Yes. So in the future projections, we've only analyzed the local wave activity because that's one we found to be like the best associated, like the anticyclonic versus the cyclonic. And yeah, when you look at the anticyclonic, you see some very strong changes in the waviness directly. There's an increase in where like California and the Great Basin region is in the USA, and quite a large decrease in the Atlantic Ocean. So kind of like following that storm track, sort of like, you know, like the tilt in the Atlantic Ocean, you see quite, in the future projections, you see quite a large decrease in the anticyclonic LWA and an increase in the cyclonic LWA, which I'm not sure 100% what that's kind of meaning, but I think it's to do with the equatorward, well, the poleward shift of the jet streams, which is sort of predicted to happen by over the 21st century in the Atlantic Ocean.
Very interesting, thank you. I don't think that I see any more questions. So with that, I want to thank you, Eliott, for the very nice and interesting presentation and something different in our session. I think with that we will wrap up this block. So if you still have any questions to our speakers, please feel free to use the chat box as well as messages on the event Mobi platform. With that, I will wrap up this block, as I said, and tomorrow we have the last block of our session, which is dedicated to information on heat waves as well as the data sets and stuff like this. We also have 4 posters associated with our session, so please feel free to check them out tomorrow morning. And yeah, thank you so much for listening, and hope to meet you all tomorrow.
Thank you.